All right, we were working in section 15.3 last time and talking about independence of paths and conservative fields. We had gotten to the point where we were going to do a couple more examples. I think we're on example number 4. Is that what it looks like? Okay, so we're going to show that the line integral is independent of path in R2 or R3, and then we're going to use a potential function to evaluate the integral. And the first one that we're going to do is actually going to be in R2, I think, and then we're going to do an example. I can't remember if it's in R3 or not. Let's take a look, though. All right, number 4. We're going to evaluate the line integral of 2x e to the x squared minus 2y dx plus 2y minus 2x dy where C runs from 1, 2 to negative 1, 1. And I was actually creating some of the notes for today's lesson in 15.4, 15.5. I can't remember which one of it is. And there's a theorem that I didn't choose to write down in this section that probably I should have chosen to write down in this section. It's theorem 13.4, I believe it is. But it's the one that says that if you have a conservative vector field, that you will have a conservative vector field when your m sub y equals n sub x, which is what we were using last time repeatedly. Do you remember us doing that and checking that out first? So there is a theorem that I haven't actually written in. It's in your book, so you're welcome to take a look at that. That actually verifies that fact. So what we're wanting to do then is we're wanting to find m sub y and n sub x. All right, so remember this. I know it's been a couple days. This is m, and this is n. So what is m sub y? Yeah, it's just negative 2, right? And what is n sub x? It's also negative 2. So this vector field is conservative. That's what that means. Okay, so since m sub y equals n sub x, the vector field is conservative. Hence, its path independent. So now what? Well, what that means is that we can try and find that potential function, right? So it says if it's path independent, and then we're going to use a potential function to evaluate. We had a theorem about this potential function. The evaluation we haven't done yet, but the potential function part of this we have. So do you remember what we do to find a potential function for this? If you don't, it's okay. So we start out by saying if the gradient of f equals our vector field f, then what we know is that del f del x is going to equal m, which is 2x e to the x squared minus 2y, and del f del y will equal n, which was 2y minus 2x. Does this look familiar? Okay, what did we do next? Now that we've got that written, I bet you know. We integrate. And we really don't have to, I mean, we can really pick, but we've tended to go with just the first one we've integrated, right? So we've said, okay, well, I can do del f equals 2x e to the x squared minus 2y dx. And then I can integrate this so that on the left I get f of xy. On the right, I need to integrate with respect to x. So what kind of a problem do we have for the first piece, the 2x e to the x squared?
E to the x squared.
Yeah, it's a u substitution, right? But it's a pretty straightforward one. You probably don't need to write it down. So this one actually is just e to the x squared because the x squared would be u and du would be 2x. And then I need the antiderivative of negative 2y, so negative 2xy, or yx if you prefer. And then what else do I need?
Plus g of y.
Plus g of y. So after I find the integration with respect to x, what do I do? Yeah, partial, right? Yeah. So we're going to find the partial derivative. So we keep going. We're integrating them and differentiating, integrating then differentiating. That's the process. So we're going to take the partial derivative with respect to y now.
Don't we set that equal to something first?
What's that?
Don't we set f of x, y equal to something and cancel that?
We will in a minute, but you're one step ahead of me. Yeah. Yes, that is going to happen next. All right, so this part's derivative is 0. What about the negative 2xy?
That's right. Okay.
Remember?
Sorry. What'd you ask?
We're taking the derivative with respect to y, partial. Negative 2x plus g prime of y. And this is where you're going to do exactly what you said, Caleb, is you're going to set it equal to the del f del y that we have up here. So 2y minus 2x. And of course, these components match. And what's left is, in fact, a function. Okay, that's a little too broad. Let me try and make this smaller. This that's left is, in fact, a function just of y, right? That's important. If it's not a function only of y, then we're going to have some problems. We don't have a potential function is what that means. And we know we're going to have a potential function here because it was conservative. Okay? So there are cases where we might not actually have that possibility, but we knew that this one was going to work out. So it better, in fact, work out. All right, so we've got g prime of y equals 2y. So what is g of y?
Y squared plus c.
Y squared plus c. All right, so I think we're ready for our potential function. What is f of xy? All right, so we combined this function right here with this piece right here, and our resulting answer is over here. So this is my potential function. Now, that's not it. That's just, I mean, that's part of what we were asked to do. We're find a potential function, then we're going to use that potential function to do what? To evaluate the integral. Okay, so this is the theorem that we introduced at the very end last time. We hadn't actually done anything with it. Let me go back to it so you can see. Well, where was it? When did I write it down? Maybe it was further back than I had expected. Here, there it is. So if we have the potential function, then we can actually find the antiderivative by using that potential function and evaluating at the two endpoints. So that's what we're going to do as our final step here. We're going to evaluate our potential function at the two endpoints that we were given. So what this means is the integral that we were looking for to begin with over the curve C of 2x e to the x squared minus 2y dy plus 2y minus 2x dy is going to equal this potential function.
First one's dx.
Oh, did I write it down wrong?
Yeah.
Thank you, Nathan. Yes, you're right. Our potential function that we just got, where to go? Here it is. I see it on my notes too. Yeah, the e to the x squared minus 2xy plus y squared. I don't need the plus c because I'm going to be evaluating in this one. And I'm evaluating at my two endpoints. And they actually tell you that c runs from the point 1, 2 to the point negative 1, 1. So negative 1, 1 is actually where I end. And 1, 2 is where I begin. So we're going to evaluate this at these particular values. So this is e to the negative 1 squared minus 2 times negative 1 times positive 1 plus 1 squared minus e to the 1 squared minus 2 times 1 times 2 plus 2 squared. Does it look okay? Did I get all the pieces in there right? I think I did. So we're going to clean up what we've got, simplify what we can, and leave the rest. So this is e plus 2 plus 1 minus e.
Shouldn't those e's cancel out?
They will, yeah.
I
Yeah, I haven't written it in there yet, but yes, they will.
I'm sorry.
No, you're fine. Minus 4 plus 4. There's a lot that's going to cancel out, isn't there? So Caleb, you mentioned the e's. What else is going to cancel? The 4s. What's my answer? 3.
Did the force cancel out the negative?
They,
Oh, wait, yeah,
they
you're right.
canceled out before that, actually. Yeah. Mm-hmm. Any questions on that one?
Can we, can you just write integral over c of f dot dr?
You could. Yeah. I was just going back to where we started, but yeah. So Caleb was just asking basically if you had to write all of this out again. And the answer is you wouldn't necessarily have to. You could put the general form of it there if you prefer. Okay, I have one more question that we're going to take a look at in this section. We're going to, I'm not sure I started down there. Let's put it up here. Evaluate the integral of c, over c, excuse me, of f dot dr. And the function we're going to work with is x of y, f of xy, is 3x squared y plus 1, 3xy squared. And c is going to be defined a little differently in the last case, which is what's going to make this problem different. C is the bottom half circle, bottom half circle, from 1, 0 to negative 1, 0. Which means that we're going to be doing what in this particular problem? We're going to be doing something with polar, right? Because we're working on a polar type of a region. All right, before we get that far, we have to figure out if this is, the directions were the same basically kind of as before. I mean, they aren't stated exactly the same, but if we're looking for this, we need to figure out if we can use potential functions. If we can, then it makes the problem easier. So we're going to take a look at that by finding out m sub y and n sub x. So what is m sub y? 3x squared looks good. And n sub x? 3y squared. And what happened? They don't equal. So just because we have this new property doesn't mean that everything follows it, right? We can't always use the potential function because it doesn't always work. I don't always have a conservative field. So these are not equal. Hence, the curve, or the field rather, is not conservative. And if the field is not conservative, we need to parameterize. And You probably knew that was coming since I sort of jumped the gun at the very beginning and said something about polar, right?
Sure.
Spelled like spelled parameterize right. I think that's right. Parameterize. Alrighty then. So, what would x? Do you want to use t or theta? Theta. Okay, that's what I wrote in my notes too. What is x of theta going to be equal to for parameterization of this one? We're working the parameterization. Cosine theta, and I don't even need a value in front of it because my radius is 1. Okay, good. And y of theta would be sine of theta. You got it. So now we're going to go back up to that original. Oh, you know what? While we're here, let's go ahead and find x prime of t or of theta and y prime of theta because we'll need them in a minute anyway. So what is x prime of theta? Negative sine of theta. And y prime of theta? Cosine theta. Fabulous. I wrote y prime and x prime, so if I change my notation, you're right. We can write that, and that might be a little bit better instead of using that notation. Yeah. So x prime of theta would be dx d theta. So if you want to write like this, you can write this.
We will need that.
I think I wrote that wrong too. I did. Yeah, we will. Okay. All right, so we're going to go back up to our original function that we were given, and we're going to put that into equation with theta in them instead. We're going to change our parameter. So what we're looking at is we're looking at an integral of c. I'm sorry, that's not written right. Over c of f dot dr, which should be the integral we started with 3x squared y plus 1 dx plus 3xy squared dy. And our angle is doing what?
2 pi to 2 pi.
Yeah, so say that again louder, Caleb, what'd you say?
2 pi to negative
I don't think you want to say 2 pi to negative pi. That sounds a little awkward. Pi to 2 pi would probably be the easier way to do it.
pi. You're going from 1, 2 to 2, 1, or negative 1, 2, and going the other direction.
Then you could say we're going from 2 pi to pi.
But wouldn't that be in the counterclockwise direction if we did that?
So your point is that we're moving in this direction, right?
Right.
Okay, but I don't think you can say 2 pi to negative pi. That doesn't work.
If
You see what I'm
went 0
saying?
to negative pi, that would work.
Yes, we could say from 0 to negative pi, but that's equivalent to saying from 2 pi to pi, so either way should work just fine. So do you want to use, how about let's just use 0 since we can. So we're going to go from 0 to negative pi. We could probably fix our parameters a little bit. Did I change that? Yeah, that's what I did. Here's how I dealt with it. This would work. I think I was modeling what the book did. They did use 0 to pi to 2 pi here. They did this. That fixed it so that the signs would actually be correct. So if you put in 2 pi or 0, we'll say 0 if you will, or I guess we'll say 2 pi. How did they write that? Oh, they used 0 to pi. That's what they used. Just to keep it simple. I did skip that step up here. So if you plug in 0 into this, of course you get 1, right, for x. And if you plug in 0 to this, you get 0, right? So that's 1, 0, which was my first ordered pair. If I plug in pi into this, oh, where'd it go? Over here. Pi into this one, cosine of pi is going to give me negative 1, and then sine of pi would give me, it would give me 0 again. Negative sine of pi would give me 0 again. So
Okay.
what is the negative doing? Do you know?
It's when you go to pi over 2.
Yeah, it's checking to make sure that that halfway point in the middle, so when we're at pi over 2, halfway between 0 and pi here, then we actually end up in that bottom part of the circle. Because right now, if I go from 0 to pi, I'm on the top half of the circle, right? And I want to make sure I'm in the bottom half of the circle, so that negative in front of the y is flipping my circle down. If you think about just like imagery of what's really going on visually, it's flipping the circle down. So if I put in pi over 2, then this one becomes 0, that's fine, but if I put in sine of pi over 2, I get 1, and the negative in front makes it negative 1. There's several ways to do that. Caleb and I are actually having a discussion about a different one in my office the other day. You're going to get the same answer if you change some of these parameters around because you've changed multiple things to get it to match up to. So that would be fine as well. So we'll go with the 0 to pi for now here. I haven't actually used my parameters. I do need a sign right here, right? That works? Okay, great. All right, so now we need to use this and we need to put our parameters in. Yeah? Okay, so we've got the integral from 0 to pi of 3x squared y. So x is cosine, so we've got 3 cosine squared of theta times negative sine theta. So I need a negative here at front. And plus 1 times dx, which is another negative, so negative sine theta and then d theta. And we'll pull the d thetas out in a minute. I mean, we can pull out now if you want, but. And then I have 3 times x, which was cosine theta. And then I've got y squared, so the fact that it's negative sine squared doesn't matter, it's going to be positive, right? So this is sine squared. Times dy, and dy is negative cosine theta d theta. That's just what I had from the previous screen. I feel like last time we ended with lots of sines and cosines where we were messing around with stuff, didn't we? We had one last time where we had lots of that going on, I think. All right, so let's clean up and see what we have. And we're probably going to end up with some sort of u substitutions going on, perhaps, right? And maybe some trig substitutions involved in there as well. And so let's just see where we end up. All right, so I've got negative sine times the negative 3 cosine, so I'm going to end up with 3 cosine squared sine squared theta minus sine of theta. D theta I'll put at the very end when I'm done. I've got now a negative 3, and I've got cosine squared theta sine squared theta, and then d theta. Did I catch everything? I think I did. Oh, beautiful things are about to happen. What are they? Well, it doesn't get much better than that, does it? Because now I don't need any of that fancy stuff that I thought I might have to do. Because that's what it looked like, right? This is 0 to pi of simply negative sine of theta, d theta. So what's the antiderivative of negative sine of theta? Cosine of theta, which we'll evaluate at pi and 0. What's cosine of pi? Negative 1 minus cosine of 0, 1, for a grand whopping total of negative 2. I wanted to purposely put this one in here because I wanted you to realize that just because we're in the section where we get to use these potential functions doesn't mean that everyone is able to be done with the potential function. Because the directions actually state it that way. If it's conservative, use potential functions to do that, which presumes that not all of them are conservative and not able to be done that way. Any questions on that one? All right, and I gave you these assignment last time. Those are the problem numbers if you didn't get those written down. Go ahead and jot those down.